This is geometry lesson 14.1. We're in the last chapter in the book. We are looking at chord length and arc measure. So we are back looking at circles. The big idea says the properties of chords in circles. We'll talk about what that means. Follow from properties of isosceles triangles. So we're going to be relating pieces of our circles and isosceles triangles. So all of our work with triangles, sine, cosine, tangent, Pythagorean theorem, 30, 60, 90s, we can now use all of that stuff inside of a circle to help us find certain lengths, certain measurements. So knowing any two of the length of a chord, the measure of its arc, and the radius of the circle, you can determine the third, because from there we can use sine, cosine, tangent, we can use Pythagorean theorem, we can use 30, 60, 90. All right, so let's take a look. So the flower fountain in Centennial Park in Holland, Michigan, I thought that was interesting that in the textbook they referred to something in Holland, is protected by an iron fence that is the shape of a regular 16 gon, right? So it's not a perfect circle. It's got 16 individual sides that are all connected. Recall that the vertices of a regular polygon, they all lie on the single circle. So there's a circle that runs on the outside of this, and you can see it's hard to see because there's 16 sides. But there's a circle that's running outside of it that does disconnect from the sides of this 16 gon. But the radius of the circle will hit on each one of these vertices. So from the center of the circle, okay, it will hit each one of these vertices, and then the circle will continue a little bit outside of the 16 gon. But at the radius of both the 16 gon and the circle, okay, they are hitting at that vertice. So the radius of the circle is the same as the radius of the 16 gon. The sides of the polygon are considered chords. Okay, so we know the circle continues outside, and then the side of the polygon is this line that connects one point on the circle to another point on the circle. We've looked at different kinds of lines that go through the center of the circle. A chord does not. It goes from one point on the outside of the circle to another point. So if we slide down real quick, just to get an idea, I want to make sure we know what a chord is. CD is a chord and AB is a chord. It's just a point out here on the side of the circle, and it's a line that connects to another point on the outside of a circle. Okay, that right there is a chord, and we're going to be looking at the measurements of these and how can we find them. What's interesting about them is that each one of them hits the side of the circle. So from the center of the circle to D and the center of the circle to C, it would be the same measurement because that's the radius of the circle. And so I'm kind of getting ahead of myself here, but when you connect those with the radius, you're creating an isosceles triangle because this and this are going to be equal, and then you're going to have this third side, which is the chord. And we know so much information about isosceles triangles that we can go ahead and find the measurement of the chord using all of those skills. So that's what we're going to be looking at mostly here today. So in general, a segment DB is called the chord of arc DB. If the center of the circle is C, then angle BCD is called the central angle, and we've looked at central angles there. Remember, the important part of a central angle is that it's equal to the arc measure out here. So if this central angle was, let's just say 30 degrees, I know that my arc measure out here, my arc BD, would also equal 30 degrees. So central angles are going to be equal to the arc measure out there. We know that. So real quick, we're not going to spend too much on those angles. We're going to be much more on the isosceles triangles. But the arc chord congruence theorem basically states what I just said. If two arcs have the same measure, they are congruent and their chords are congruent. So if I have CD and I knew that CD, the arc measure, was say, I'm just going to make up something here, 65 degrees. And let's say AB, the arc measure, remember that's the distance here, or what portion of the circle it takes up, total of 360, is also 65 degrees. If I know that that's true, if two arcs have the same measure, the arcs are congruent and their chords are congruent. So CD, the line CD, is going to be congruent or equal to AB if I know that the arc measures are the same. So if they create the same arc measure, that means the actual length from C to D and A to B is the same. That's what part A is stating. If two chords have the same length, the minor arcs have the same measure, so we can go backwards. If you know that CD is congruent to AB, I automatically know the arc is equal to the arc. All right, so that's what we know about the arcs based on the chords. Here's the more important theorem. So like I talked about, if you have this chord AB, goes from one point on the circle to another point on the circle. If I go from the center to A and the center to B, that is the radius. And so it's going to be equal. So it creates this isosceles triangle that we know a lot about. Okay, we're going to run through this in a second, but what do we know about an isosceles triangle? We know that the height of an isosceles triangle is the perpendicular bisector of the base. So if this is an isosceles triangle, AOB, if this is the height, it's the distance from this point to that line. It's going to bisect this base or this chord into two pieces. It's also going to bisect this angle. You're going to get two equal angles there. And the opposite of all that is true. If I have this triangle and I know that it's bisecting this, then I know that it's going from the center of the circle through it. That's basically what this is all going to say. So let's run through it. So this theorem says the line containing the center of a circle perpendicular to a chord bisects the chord. So that's just telling you, all right, I've got this isosceles triangle from the center of the circle. The point that hits this at 90 degrees is going to bisect AB. We already covered that. Number two, the line containing the center of a circle and the midpoint of a chord. So this is the midpoint because it's bisecting it. It also bisects the central angle of the chord. And again, the reason we know this is because these are properties of an isosceles triangle. So we know that the central angle is going to be bisected here. If we know that the angle is bisected, we know that the chord is perpendicular to this line, and it's going to bisect the chord. So now we're just going backwards. So if you see that this is hitting at 90 and bisecting this, we know these angles are equal. Or if they give you that information, these angles are equal, then I also know that this is true. So they can give you one or the other, but they create each other. The perpendicular bisector of a chord of a circle contains the center of a circle. So if they draw this picture and I know that this is hitting at 90 degrees and it's bisecting it, then I know this line goes through the center. If you were ever judging, does that line actually go through the center of the circle? Well, if it's hitting a chord at 90 degrees and splitting it, then you do know that it goes through the center. All right, so a lot of that gets really wordy and thrown at you at once, and it seems like a lot, but that's really just hitting all the things we already know about an isosceles triangle. So as we work through this, it will just make sense based on our previous knowledge. Okay, so example one. Like we talked about, we're going to create these triangles, and we now know 30, 60, 90s, Pythagorean theorem, and even sine, cosine, tangent will help us find sides and angles and other stuff like that. So we're going to use all that information here to solve for missing pieces. So we have a chord that's 13 centimeters long. So the only chord in this picture is NM. So NM equals 13. And I've provided all the pictures here for you. They're not always going to do that. So you're going to have to draw your circle. They're going to say a chord is 13 centimeters long. So you're going to draw a chord. You're going to label it 13. And it lies in a circle with a radius of 10. So from the center to any point on the side of the circle is 10. But we're specifically going to draw the radius that goes to the endpoint of these chords. And therefore that's 10. So you could draw this yourself. You draw a chord. You label it 13. Then you connect it with a radius to each endpoint. And those are 10. How far is the chord from the center of the circle? So that would be this measurement right here. When we measure distance, it always has to hit at 90 degrees, right? We don't measure diagonally. That's not the distance away. It's not 10. It's to the line 90 degrees. That's the distance it is away. So we're going to go ahead and try and find this. Now, first of all, based on our theorem on the last page, because this is an isosceles triangle, if this is coming down at 90 degrees, we know it's bisecting this base right here. So if that's 13, I'm going to do 13 divided by 2, and that's 6.5. So I know that both of these pieces down here are 6.5 and 6.5 because that's what's true in an isosceles triangle, and that also goes back to the theorem on the last page. Now, I'm just going to go ahead and highlight this. We have a right triangle with a hypotenuse of 10 and a side of 6.5. We have enough information to find this right here. You could try and use sine, cosine, tangent because we just did that. That's not going to help you find this side right away. You have to find an angle and then use that angle. So that's going to be multi-step. We don't appear to have a 30, 60, 90. There's nothing special in the relationship from 6.5 to 10. I don't see a 3, 4, 5 or 5, 12, 13. But what I do see is just two sides, and we always kind of forget about the most simple way to find the third side of a triangle is Pythagorean theorem. Okay, so if I have two sides, one of them being the hypotenuse here, I can set up a squared plus b squared equals c squared. That always works. It's so simple we forget about it sometimes. So I'm going to go ahead and plug in 6.5 for b, and then I must put c as 10. And we've talked about we don't actually need to expand those anymore. We can just minus 6.5 squared from both sides, and the calculator will handle that for us. So we're going to have a squared equals, now you can go ahead and expand them if you're more comfortable, but you can do 10 squared minus 6.5 squared, and that'll get you your answer there. So 57.75. That would be the same as if you did 10 squared is 100 and 6.5 squared is whatever it is, and then minus it. You'd still end up at 57.75. And then we know, of course, we're going to square root that. So a is going to equal square root 57.5. You can see that's about 7.6. Let's put the squiggles for about 7.6. That's the measurement that we wanted there. So this is what OL is equal to. And of course, that's centimeters, but the 7.6 is what we're really concerned about right there. All right, so there's one example of how we have a chord. We know that if we connect the center of the circle to the endpoints of that chord, we create an isosceles triangle. In this case, we had enough information to use Pythagorean theorem. So now let's take a look at some other ones that we're going to use, maybe sine, cosine, tangent, or 30, 60, 90s, or anything like that. So example 2. So this person wants to hang a string of lights on the fence around a flower fountain. So this goes kind of back to what we're looking at here. We've got this fence. It's a 16 gon. That's exactly what we have here, which means there's actually a circle that just goes around the outside of this. It does disconnect from that 16 gon where the sides are, but at the vertices they are touching. Okay, so what we need to recognize here is this to here is the radius because it's hitting a vertice. This to B, that's the radius because it's hitting a vertice. But C to M is not going to be the equal length there. C to M is like O to L. But because we have 16 sides, it's very finite in how far it is from the edge of the circle, so it's not as obvious. But OL, right, is the distance from the center to the chord. CM is the same thing. It's the distance from the center to the chord AB, because each one of those is a vertice of this circle here. So the fence has 16 sides. The radius of the circle is 15. So I know AC is 15 and I know CB is 15. I don't know what CM is. Okay, that's going to be the measurement from the center to the chord. How long of a string of lights will she need to go once around the fountain? So she's going to string the lights not on the circle that we drew, but on the fence. So basically, I need to figure out what is the length of each one of these sides, and then just times it by 16, because she's going to hang the lights on this side, and then this side, and then this side. So it's going to be the length of a side 16 times around. So we're going to focus here on our isosceles triangles here and try and figure out what is this length, that chord AB. If I know what AB equals, I'm just going to take that length and times it by 16, and that's going to give me the full length around this shape. Okay, so working with this, we don't have enough information currently to figure out anything, right? We have one side of a triangle. That's not enough information. You need at least two things. You need an angle or you need another side. But we have enough information to find an angle. If we go back to our central angles theorems way back when, we know a full circle is 360. And so because this connects to A and B, that'd be like if we drew these all the way around and we cut this into 16 pieces, right? If we drew a line to each vertice and draw that radius, it's going to cut it into 16 pieces. So we're taking 360 and we're cutting it into 16 pieces. You go ahead and divide that, and that's 22.5. So each one of these is 22.5. We've done this kind of before. But now this line, CM, is going to bisect that. This is an isosceles triangle, so we know this height is going to bisect it. So 22.5 divided by 2 will get us each one of these little angles because it's being bisected, right? This is the apothem. We've looked at that before. So when we divide that by 2, that's 11.25. So that's the angle that's in here. So I'm going to go ahead and draw one of those triangles. Let's label it so we know what we're looking at. This is CAM, just to the 90, not all the way to B, just this right here. I know that this is 15, and I just figured out that this angle is 11.25. Now I have enough information to find AM. If I find AM, I can double it to get AB, and I can times it by 16 to go all the way around. So when I have an angle, not a special angle, just 11.25, and I have a side, I can go ahead and use sine, cosine, tangent to find my missing side. So from this angle, I have opposite and hypotenuse. That would be sine. So I'm going to do sine of 11.25 equals opposite over hypotenuse, x over 15. That's in the multiplying spot. So I'm going to go ahead and do sine of 11.25 times 15. So that length is about 2.926. I'm just going to leave it in the calculator though. So that's the length from A to M. But I need from A to B to get the full side, one side of this 16 gone. So I'm going to go ahead and just double that. All right, and I get 5.8. And that means that AB right here, so I times this by 2, and that's going to equal AB. That's approximately 5.85. Let's do times 2. Just want to make sure we write that out correctly. So 2.926 times 2. So you know what you did when you look back at your notes. 5.85. Now you don't have to write all these down, right? I can just keep this in my calculator. So I use this little triangle to find out that this right here, this piece from A to M was 2.926 about. I doubled it because I know that this is an isosceles triangle and AB is being bisected by the height. So I double it. That entire length right there is about 5.85. And now I'm going to times that by 16. Now I'm not going to use my rounded answer. I'm going to go ahead and just leave that full answer in there and hit times 16. I will get a much better answer. You could, of course, have rounded this to 2.92 and then just doubled 2.92. You'd get a little bit different answer than this. And then that answer, you could round it and then times that by 16. But every time we round in the middle of a question, it gets our answer, final answer, a little farther off. So it's better to just keep it in the calculator, double it, times it by 16. Now we have a much more exact answer. We'll, of course, simplify this one and round it. So 93.64 would be your final answer, the distance all the way around. Okay, so here's an example of how we're going to use sine, cosine, tangent to solve one of these. And then on the very bottom here, we're going to look at special triangles, 30, 60, 90s, how they play in. Now, if you're really bad with your special triangles and you really like sine, cosine, tangent, you can always use it. It's going to work. You can put sine of 30 and sine of 45 and all that stuff in your calculator, and it will work. So you don't have to use the special triangles. So let's look at these special situations here. Again, I've given you the pictures. You may have to draw these yourself. So you would have to draw a circle. There's a radius of 25. You would have a chord that's connected, and each radius to the endpoints of that chord are 25. And then the measurement of the arc that it's creating is different in each example. So find the length of a chord of an arc with the given measure. So here we have a 60-degree arc. So if you were going to draw this, you know what 90 looks like. 90 is 1/4 of your circle. So 60 is going to be a little less if you had to draw this yourself. The endpoints for all of these are going to be 25. The radius of all the circle is always going to be 25. And we know if the arc is 60, the central angle is 60. So we're trying to find the length of the chord. So AB in this picture, CD in this picture. Final answer is going to be AB equals this, CD equals this, FE equals this. And they're all going to work a little differently depending on the angles that we've got. So right here, we've got, of course, an isosceles triangle. And if it's isosceles, we know that these two angles are equal to each other. So if this is 60, I have 120 left over that has to get split two ways. So I know all of these angles are 60. Well, if all the angles are 60, that means all the sides are the same. So AB is 25 because I have an equilateral triangle. It is isosceles, but it's actually equilateral. Let's say you didn't catch that. You go ahead and you draw your little altitude here, and then that's going to cut this 60 into 30 and 30. And so what we're creating here, if this was O, and then we've got this other point, let's call that X. Point X and B, we've now created a little 30, 60, 90 in here. We know that this is 25. And what we're looking for is this little piece out here across from the 30. Well, this would be your X and your 2X. We don't need the X radical 3, but that's where it would go. So if we're looking for X and this is 2X, you would take half of 25. So 25 divided by 2 is 12.5. So I know that this is 12.5. So I know this is 12.5. And then if I double 12.5 times 2, that also gets me to the 25. So it would get me there. Okay, so what you could also do is use sine, cosine, tangent in this case. So I've got the opposite and the hypotenuse from my 30-degree angle. If I wanted to use sine, cosine, tangent, that would be sine. So one more way to do this, again, I would use the equilateral triangle if I saw it. If not, I would use my 30, 60, 90 because it's faster. But if you always like to use sine, cosine, tangent, it's always an option. So I have my opposite and hypotenuse. So I would say sine of 30 equals opposite x over hypotenuse 25. And if I go ahead and punch that in, sine of 30 times 25, sure enough, I get 12.5 for this as well. So you can do 30, 60, 90. You can use sine, cosine, tangent. You could use your knowledge of isosceles and equilateral triangles. In the end here, we ended up with 25. So when you have a 60-degree arc, a 60-degree angle, it creates all these different opportunities for you. So what happens when we have a 90-degree? All right, so if you had to draw this yourself, you draw a circle, you've got your arc from C to D. They're telling you that the arc measure is going to be 90, so you want to make sure that you're creating a 90-degree angle in here, which is going to create a 90-degree arc on the outside of the circle. This whole problem, the radius of the circle is 25. So from the center to each endpoint of your arc of your chord CD, you're going to have 25. So we know that this is isosceles. So we know that these two angles are equal. So if this is 90, then these must be 45 and 45, which means this is an x radical 2. So if it's 25, 25, I know that CD equals 25 radical 2. And if I was giving a measurement rounded to the nearest tenth or something like that, I would do 25 radical 2, and it's 35.4. Okay, what if you didn't catch the 45, 45, 90, or you just don't like using those? You can't remember what those look like. That's okay. You can do a squared, b squared, c squared. You could do 25 squared plus 25 squared equals c squared. Your c would have to be the hypotenuse, which we're looking for. So 25 squared plus 25 squared is that, and then you would square root 1250. Sure enough, we get the same answer. You could also, if you recognize it's a 45, 45, but you're just not comfortable using the x radical 2, you could say, okay, so from my 45, I've got the opposite and I've got the hypotenuse, or I've got the adjacent and the hypotenuse. So let's use cosine just to change it up. Cosine of 45, let's say this 45, the adjacent would be 25, and we'd be looking for the hypotenuse, adjacent over hypotenuse. Or you could have done sine of 45, would be opposite over hypotenuse, would also be 25 over. And in this case, we know we would go ahead and flip these. We'd put x up here, cos of 45 down here. We're solid with this work now. So 25 divided by cos of 45 also gives me the same answer. So you can see 3 different ways to do this. Special triangles, definitely the fastest. Pythagorean theorem, pretty easy. Sine, cosine, tangent, more likely that you're going to make a mistake on this problem, but it obviously works. So if you fall in love with one of these, you can always use it. All right, but it is helpful to have all 3 tools in your tool belt and then be able to pick the one that gets you there the easiest and the fastest. All right, so last one, if you had to draw this yourself, You have a circle, and we're going to draw a chord where the arc measure, which also means the angle measure on the inside, is 120 degrees. So if you were drawing that yourself, think of a 90, make it a little bit bigger. We connect those two endpoints of the chord FE. That's what we're looking for. What's the length of FE when I have an arc measure of 120? The radius of each here is 25. And so because I have a 120 in here, that's not creating a special triangle. But if I go ahead and draw the line, which is the height of this isosceles triangle, I know that it splits that 120 into two equal angles. So now I have a 30, 60, 90. So if I go ahead and pull out one of those 30, 60, 90s, this is FGO. This is my 60. I know that this is 25. This is my 30. So if I'm trying to find FGE, that length all the way across, I need FG, which in this case is across from the 60. That's the x radical 3. This would be the x, which I don't need. This would be my 2x, right? So if this is 2x, x would be half the size. You would do 25 divided by 2. So I know that this is 12.5, which means this side right here, my x radical 3, is going to be 12.5 radical 3. All right. That would equal, let's go ahead and get the decimal version, about that, 21.65. That's just halfway across. So that's from F to G. I'm looking for FE, the entire chord length here. I would just times that by 2. I wouldn't round it first. I'd leave it in the calculator. So my final answer here now, 21.65 times 2 gets me 43.3. All right. And I think that's the easiest way to do that one. For the sake of practice here, let's talk about, could I have used sine, cosine, tangent? Well, you couldn't use Pythagorean theorem. Some people want to say, well, can't you do 25 plus 25 squared equals c squared? But this bigger triangle is not a 90-degree triangle. That only works in right triangles. So be careful. You can't use Pythagorean theorem unless it's a 90-degree triangle. Inside this little one, you could use it if you had two sides, but we don't. We only have the 25, and we have an angle. So that's enough information to use sine, cosine, tangent. So if I was going from the 60, I'm looking for the opposite out here. So that would be sine, because I'm going to use opposite and hypotenuse. Sine of 60 equals x over 25. I would be multiplying here. So sine of 60 times 25. Once again, gets me that 21.65 for FG, times it by 2, and there you go. So you could have used sine, cosine, tangent if you don't like your 30, 60, 90s. They will all work, so we're going to practice using all of our skills here in this section.